we continue review linear algebra. Determine whether the set of vector is orthogonal. So we have three vectors. So basically, we just need to check three pairs to see if they are orthogonal. So let this be U1, U2, and U3. Just find the product, the dot product, or the inner product of each pair. Right, U1, U2. I'm just going to write the vector as the bracket notation. 3, 6, 3 dot -3, 0, 3. So 3 times -3 plus 6 times 0 plus 3 times 3. So that's 0 minus 9 plus 9 is 0. So if the dot product is equal to 0, the vectors are orthogonal. So we have U1, U2. Now we check for U2 and U3, just the dot product. -3, 0 and 3, 3, -3 and 3. -3 times 3 is 9, 0 plus, -9, -3 times 3, so -9 plus 0 plus 9. Of course, that is equal to 0, so they are orthogonal as well. And now we check U3 and U1. The dot product the order doesn't really matter. U3 dot U1 or U1 dot U3, it doesn't matter. So 3 and 1, 3, -3 and 3 dot 3, 6, 3. So -9, positive 9 minus 18 plus 9, and that is equal to 0 as well. So U3 and U1 are orthogonal. So determine whether the set of vector is orthogonal. The answer to that is yes, because we have three pairs and each pair of the vectors are orthogonal. So the answer is yes, they are orthogonal. Right. Next, determine express the vector x as a linear combination of u known that u1, u2, u3 is an orthogonal set. Now usually if we say x is a linear combination of u1, u2, u3, we just go ahead and say a1 times u1 plus a2 times u2 plus a3 times u3 equal to x, and we just solve the equation. That should be very easy. However, knowing that the vector are orthogonal, there is another way to do this. And actually, if we do it by hand, it will be more efficient than solving this system of equation, which will involving row reducing, which may take some time. Now, if the vector are orthogonal, then there is another way to do that. So if x is a linear combination of those vector u, so we can write vector x is equal to the projection of x on vector u1 plus projection of x on vector u2 and projection of x on vector u3. And the dot product, even though we can do by hand, but it's better if we can use the calculator, be more precise. So it's less room for error. That's what I want to say. So projection of x onto u1 is vector x dot u1 over u1 dot itself in the direction of u1. Now we do the same thing. X dot u2 over u2 dot u2 multiplied by u2, and then x dot u3 over u3 dot itself in direction of u3. When we write this, we can put this coefficient, so which give us the linear combination of the vectors. So we just do this pretty much. So usually this time problem I will work using list. Like this is the list of numbers. I use L1, L2. Right, so we use this key, comma, second the parentheses give us the bracket. So bracket u1 -2, comma 0, comma 1, close, store into L1, 3, comma 5, comma 6, close, store into L2, and then -2, 6, and -4, close it, store into L3, and with the x I will store into L4. Right, now we're going to do this. Alpha y equal to fraction. This is the dot product is the sum. So second stat, go to math, option number 5. So sum L4, second number 4, second number 1. Yeah, so that is dot product of this 4 and this 1, which is u1 and x. At the bottom is also sum second stat, sum L1 times L1. Do that, and we have 5. Times u1, and then we do this. Since we have that already, all I just do is just highlight it and change the L1 to L2. And we have 2, U2, and then I just highlight it, hit enter, change to L3, have -4. Yeah. So we do a lot of dot product. The dot product, of course, we can do by hand like this, or we can just use a calculator. the sum of the two lists times together. That gives us the dot product. Right. We do a lot of this. Let W be the subspace spanned by U. Write this Y as the sum of vector in W and vector orthogonal to W. So Y will be as the sum of the vector in W and a vector orthogonal to W. So just draw the sketch first. So this is the space of W. On that, there are two vectors. And then we write the vector Y, which is outside like this. For Y, we can find the orthogonal projection. That is the Y hat, the orthogonal projection. And then subtract them, we have the Z, just distance between them. Right, now, so pretty much we do the same thing. Y hat will be projection of Y onto U1 plus projection of Y onto U2. So which is Y dot U1 dot itself in direction of U1 plus Y dot U2 dot U2 in direction of U2. Right. So let's just put all the numbers here for one, and we still use a calculator. So Y is positive 12, 14, and 25 dot U1 to negative 1 all over U1 dot itself. As you see, even write in them out. Take the whole line, maybe more, and then times the vector U1 to negative 1. Right, so that's the first one. And then the second one, 12, 14, 25 dot U2 negative 1, 3, and 4, negative 1, 3, and 4, negative 1, 3, and 4. The vector is negative 1, 3, and 4. Right, like I said, we're not going to use a calculator. We're not going to use do this by hand. So we just have find L1 vector 2, and negative 1 store into L1, negative 1, 3, and 4 store into L2. And then we just, we still need Y. Let's store that into L3. 12, 14, and 25. Store that into L3. Right, now we just do all of this. Let's do that again. Second stat, Go to math, option number 5, summation of y and u1 to L1, L3, L1, second 1, second 3. Or we say 3 and 1, doesn't matter. Over second stat, sum of L1, L1 times L1 plus, actually we can do this, so we just hit enter, free for now, and then copy, then plus, copy again, now change the L1 to L2. Alright, so we'll do all of that. We have 1, 21 and 17. And then the z, so this is the vector y that belongs to W. Now to find the vector orthogonal to W that decompose to get to z, to get to y, sorry. We can say we will write y as the sum of the vector that is orthogonal to W and the vector that is in W. So we're going to say y hat, sorry, there's only one hat here. The y is the actual values, y hat is in W, so we have y equal to y hat plus z. So z is equal y minus y hat, y 12, 14 and 25 minus y hat 1, 21, 17. So that 11, negative 7 and 8. Yeah, of course we just set L3 minus this. I guess we can't. Do all of that. Yeah, still works. Right. So that is decompose a y into y hat in W and z orthogonal to W. Z is orthogonal. We can say orthogonal to W. Right, next, find the closest point y to the subspace spanned by U1, U2. So pretty much we do the same thing here. The closest point is going to be y hat. So we're just going to say it. Y hat is equal to projection of y onto U1 plus projection of y onto U2. Right, projection is y dot U1 over U1 dot itself times U1 plus y times U2 over U2 times U2. Right, just going to store all of this into the calculator. U1 is L1 1 comma 0 comma negative 1. Store to L1. L2 is 2 comma 1 comma 2 store to L2, and L3 we use for Y 15, 1 and 7. Right. So we're just gonna enter that, and of course we can just copy the formula, which is exactly like that. So this is, let me look at that. So this is the dot product of L3 and L1, which is Y and U1, and then U1 dot U1 times U1, and same thing here for L3, L2, Y, U2, U2, U2 times U2. Right, 14, 5 and 6. Yeah. So utilize the calculator to find the dot product. In that case, there will be less room for error, which is almost always a good thing. Right. Now we will use more of that. This time what we do is the Gram-Schmidt process. Definitely you will see this on the test because it's one of the important concepts here. So I suppose you have the basis. Now the Gram-Schmidt process is to produce orthogonal basis or orthonormal basis. This is just orthogonal, meaning perpendicular. So the Gram-Schmidt process is as follows. Two vector like this, we set the vector v1 equal to x1, and after that we say v2 is the difference of x2 minus projection of x2 onto v1, and then v3 will be equal to x3 minus projection of x3 onto v1, and minus projection of x3 onto v2. So once we have a vector, we just find the projection onto that vector and subtract from the original x. So that's what we have. So in this case we only have two vectors. So the first one, v1, is equal to x1 is equal to 4, -2 and 0. And then so we found v. After that we just take x2, subtract the projection onto v1. That's the first step. Second step is v2 equal to x2 minus projection is x2 dot v1 dot itself in the direction of v1. Right, so I'm going to enter this into L1. And then 10, -30 and 2. Store that into L2. Store first, second 2 for L2. Right, so we have that. Now we're going to take L2 minus the projection, which is a dot product. Second stat, go to math, option number 5. So summation of x2 and v1. So L2, L1 divided by v1 v1. Second stat, sum again, L1 L1 times L1. Right, so I have negative 10, negative 20, and 2. So the Gram-Schmidt process gives us two vectors. By the way, usually when we do this, it's a good habit, just store that into L2. So V1, V2. Yeah. So we can write the basis as 4, negative 2, and 0, and negative 10, negative 20, and 2. So these two bases are orthogonal to each other. Right, now what do we do when we have three vectors? Well, same way. First we say vector v1 is equal to x1. We'll write this sideways. And then v2. Now from v2 minus projection of v2, I'm sorry, of x2, we don't have v2 yet. So v1 is x1, the original vector. Everything else will change. So x2 minus projection of x2 onto v1, because we just have v1 here. Right, so you can leave that at that. v3 is going to be projection x3 minus projection of x3 onto v1 minus projection of x3 onto v2. So if we write it out, x3 minus x3 dot product of v1 over v1 dot itself, and all of that still times v1 x3 dot v2 dot itself in direction of v2. This is v1. Right, so I'm just going to use calculator here. Store the matrix alpha zoom. This is 4 row 1 column. Zero, 1, negative 1, and 1. Store that to L1. Sorry, we use the list for right. So we use list. And then second, 1, 1, negative 1, negative 1. Store to L2 and store to L3. So that to L3. Right. Now we're going to do this. So list 2 minus orthogonal projection. So it's going to be L2. Sorry. sum of L2, L1, just going to write it out, x2 minus x2 dot v1 over v1 dot v1 v1. Second step, v1 v1 in direction of v1, right? And we have that, and then we store into L2, and we have that. If we want to, we can normalize this, or if we want to, we can just multiply something to eliminate all the fraction. So actually, if we have a calculator, we're just going to keep this, right? So whatever the answer is, we store to L2. Now go on to L3, which is the L3 minus sum L3 L1 over L1 in the direction of L1. Actually, I think we entered this earlier. We can just copy and paste, but I want to type that again. Sum L3 L2 L2 times L2, sorry, and you have that. Again, once again, if you want to write as a fraction, you can always multiply all of them by something to eliminate all the fraction. Actually, I can do that. So we can choose the first one is 0, 1, -1, and 1. This multiply by, just going to multiply by 3. That gives us 3, 2, -2, and -4. And all of this multiplied by 11 to eliminate fraction. Yeah, in that case we don't have fraction anymore. So that is the Gram-Schmidt process. Of course, if we normalize these vectors, we have the orthonormal basis. Right. Next, we find the QR factor. QR factorization, of course, we have the Q, and then we have the R. So the Q first. The Q, which is the orthonormal basis for the columns of this. So first we do the step 1. Gram-Schmidt process. and to obtain orthonormal basis. Right, so V1 is x1, 6, -3, and 0. V2 is just x2, which is this second column, minus projection of x2 onto V1, V1 dot itself in direction of V1. I'm going to store the matrix, store the list. 6, -3, 0, store onto list 1. -6, 18, and -6. Store onto list 2. Right, so we have that first one, and then I'll get lazy. I'm just going to copy and paste. Right, that one. Right, 6, 12, and -6. So that is the Gram-Schmidt process. We have, in order to get the orthonormal basis, we have to normalize it. So we say U1 is V1 over V, magnitude of V1, right? So 6, -3, 0, divided by the magnitude of it, 6 square plus -3 square plus 0 square. So that gives us 6 square has 45. So we have 6 square 45. Actually, we should simplify just one bit. So 1 over square root of 45. And then the vector. So 6 divided by square 45. By the way, square root of 45 is square root of 9, and square of 5, which is 3 square root of 5. Now we take 6 divided by that. 6 divided by 3 square root of 5 is 2 square root of 5. I mean, 2 on the top divided by square root of 5 at the bottom. And then -3, 3 and 3 cancel, so -1 over square root of 5, and then 0. And then U2 equal to V2 over magnitude of V2. So we normalize it. -6, 12, and -6. It's not 16, right? Yep, just -6. Square root 6 square plus 12 square plus -6 square. 6 square plus 12 square. 6 square plus 12 square plus 6 square. 216, or 216 is 6 square root of 6. Square of 216 is square root of 36 times square root of 6, which is 6 square root of 6, or 6, 12, negative 6 equal to 1 over square root of 6, 2 over square root of 6, and negative 1 over square root of 6. So that is U1 and U2. The next step is find the Q and R in the factorization. Right, Q. Q is just stacking the U1 and U2. It's column. Everything will be that big matrix. Because they're a fraction. So that is Q. And next, if we have QR equal to A, then multiply by inverse on both sides. So that cancels out, and we just have R equal to Q inverse times 8. Q inverse, actually the properties, Q is orthogonal matrix. Q times Q transpose equal to identity, meaning that Q transpose is equal to Q inverse. So with that, we say A R equal to Q inverse, which is Q transpose A. Turn it this sideways. And then 1 over square root of 6, 2 over square root of 6, then 1 over square root of 6, Q transpose, and then A. Like that. 6, negative 6, negative 3, 18, 0, and negative 6. So when we multiply this, R is going to be a 2 by 2 matrix. So 6, that's 12 square root of 5. Plus 3, so it's 15 square root of 5. And then next, that's negative 16, negative 12, so negative 30 square root of 5. 6 square root of 6, negative 6 square root of 6, and 0. And finally, negative 6, 36 minus 6, so that's just 36 square root of 6. Negative, right? Oh, I forgot the negative here. Wait. What is L2? Never mind, this is correct. So, negative 30, negative 6, and negative 6. And then we have 36. 36, that will be 36 minus 12 will be 24. Negative 6. Sorry. negative 6, 36 plus 6, so 6 and minus 6 cancel, so that's just 36 over square of 6. Right. Next, least square solution. Least square solution of the inconsistent system x equal to b. So we're going to use the normal equation from this, turn into a normal equation of A transpose A x equal to b. Sorry, A transpose. Multiply A transpose on both sides. And the solution there's going to be with a hat instead. So multiply inverse. So we have x hat equal to A transpose A of that inverse times A transpose times B. So that is the least square solution to the system. So I'm just going to enter this to matrix. Three row, two column. One, two, three, 4, 5, and 9. Just hit enter. So when we hit enter, we store this value into the answer. So if we want to recall it, just second the negative sign, and I will transpose second matrix, transpose, and the matrix itself inverse the matrix again, transpose, and then times B. This is B. Right. So with that, we should convert this to fraction. Right, 19 over. So x hat equal to 19 over 18 and negative 7 over 18. Right, just that. So that is the solution to the least square problem. Next, given A and B, determine the least square error of the least square error. Well, first we will find the least square solution. From here, the least square solution, we skip the intermediate step. X equal to A transpose A, or that inverse times A transpose B, and the least square error least square error is pretty much this equation. We find that to be the least, and the least would be where it is the B hat. Right, so pretty much we'll do that. So let's store the matrix A. Four, 3, 2, 1, 3, 2. So just hit enter, and now I'm just going to enter this. Open parentheses, A transpose A inverse A transpose, and then B. With that, let's convert to fraction. 1/3, 2/3. First, the least square solution is A transpose A of that inverse times A transpose B. If we do that, we have 1/3 and 2/3. And the least square solution, least square error, we're just going to do that. A x hat minus B. So first we're going to take A times x times that. That's the last answer. Subtract 36 hat, subtract B. 4, 2, and 1. Right, so we have that. So we have the magnitude of -2/3, -2/3, and 4/3. To just find the norm length of that matrix. Right. So another way to find this is just the norm square root of the dot product. The dot product. Oh, I see. That's not a list, so we cannot sum like that. And we'll just do this by hand then. Square root -2/3 plus -2/3 square plus (4/3) square. I don't think that is any nice number, so we're just gonna keep in the spirit of approximation. We use a decimal as a approximation. Alright, go to the next one. Find the equation y equal to beta naught plus beta 1x of the least square solution. Well, this is exactly what we just did, right? If we find the least square solution of x beta equal to y, then the least square solution is b hat equal to x transpose x inverse x transpose y. Right, pretty straightforward. Right, the matrix 4 row 2 column. 1, 1, 1, 1, 2, 3, 7, and 8. Right? I'll just have to hit enter. Getting lazy here. Okay, hey. Right. What I have is answer transpose, answer to -1, answer transpose. And now we enter y, just for row 1 column. 1, 2, 3, and 4. So like that. So usually for this problem, the answer is not going to be anything nice and even. Sorry. Just convert that. To fraction. Actually, it does. So we have b hat is equal to 5/13 and 11/26. So the equation is y equal to 5/13 plus 11/26 b x. Sorry. So this is the equation of the best fit line. So very simple. Now let's see if we don't not given this. Of course, to construct the x and the y, very simple. Yeah, on here need to show works. We still do this on the calculator, but want to show work of setting up the x and the beta and the y. So x will be 1 on x values, -5, 1, -3, 1 and 4, 1 and 1, 1 and -1. Now the beta is of course it's beta 1, beta not. So that's not important. So we need the x, and then the y is just the y values. So solution beta hat equal to x transpose x, or that inverse x transpose y. There's no y hat here, sorry. Actually the solution will be y hat, but this is the original y values. Alright, so x, just enter that matrix. Five row, 2 column. Okay, right. 1, 1, 1, 1, and 1. Now the x values: -5, -3, 4, 1, and -1. Right. And I will do this. Just need to change the y values. -10, -8, 9, 1, and -2. Can we change it to fraction? Yes. But of course we can just keep it like that if we want to. But bottom line is, we find the beta hat is equal to -17/61 and then 525 over 244. And so the equation is y hat equal to negative 17 over 61 plus 525 over 244 y x, sorry. Yeah. Oh, because they said round to the nearest thousand. Or we write this as negative 0.279 plus 2.152x. Find the sum of the square residuals. I'm just going to keep that. Oh, I forgot the times there. Right. The data up below are one-way commute times. So we have in minutes. So the x is in minute. The y will be the number of absence. Find the equation of the regression data. What will be the predicted number of absence if the commute time was 95 minutes? Is this a reasonable question? Right. So usually for this, if we construct the matrix just like that, remember, when it alpha zoom, it only go up to 6. So we cannot really do that on a big home screen here. So the matrix will be big. So in that case, what we use is just go with the list. By the way, if you want to clear the list, never hit the delete button. Only highlight it, clear, and enter. Highlight the list, clear, and enter. Clear, and enter. Right. And the values 72, 85, 91, 90, 88, 98, 75, 100, and 80. Right, y 3, 7, 10, 10, 8, 15, 4, 15, and 5. Right. So I have all that in. List 1, list 2, quick. Or you can just enter the numbers and then store to list 1, list 2, same way. But what is more important after this is hit stat and go to either option number 4, option number 8. Once again, stat, go to calculate either 4 or 8. Just going to use 4 here. L1, L2, right? Good. Right, so that is the equation. So we have y hat. According to that, we can say ax plus b. So 0.448536. Just going to use a bunch. To the nearest 100. So read that part first. 0.45 x b minus 30.27. Right, so that's y hat. Now predict if the commute time is 95 minutes. So when we substitute x equal to 95, y hat is equal to 0.45 times 95 minus 30.27. 12.48, so about 12. To nearest whole number, so 12, and the unit will be absence. So if the commute time is 95 minutes, there will be 12 absence during the term. Right, so that's reasonable. Well, it is reasonable because the 95 is missing from here and it is within the range. If I use like commute time is 3 hours or 180 minutes, this is way out of this, so that would not be a good choice here. Right, so that's pretty much that. Next, orthogonally diagonalize the matrix, giving an orthogonal matrix P and the diagonal matrix D. Right, so this just find the eigenvalues, eigenvectors, and decompose it because we still diagonalize it, right? So first step, eigenvalues, which means solving the equation of determinant of A minus lambda I equal to 0. So determinant 2 minus lambda 2 and 2 5 minus lambda, that has to be equal to 0. So 2 by 2 determinant should be simple, so cross multiply 2 minus lambda 5 minus lambda minus 4. So that gives us 10 minus 2 lambda minus 5 lambda minus 7 lambda plus lambda square minus 4 equal to 0. So lambda square minus 7 lambda plus 6 equal to 0. So that looked like, if I'm just going to solve that, graph it quickly. I think solution is 1 and 6. X squared minus 7x plus 6. See the graph? To go to 1 and 2, 3, 4, 5, 6. It's 1 and 6. Let's denote this is 1, this is 2. Right, so that is the eigenvalues. Now the eigenvectors. Eigenvectors is solving the equation A minus lambda I V equal to a 0 vector. So first for the eigenvalues of 1. I'm going to just do this, the matrix. 2 eigenvalues is 1, so minus 1 on the diagonal. So that A minus lambda I times V equal to 0. So that means you write this as 1, 2, 2, 4 on metric matrix, and then reduce to echelon form. For this easy, I can just do it by hand. Multiply negative 2 to row 1 and add to that. This will go to 0, right? So from here we say V1 plus 2V2 equal to 0. V2 is 3. So we write the solution as V equal to V1 V2. V1, if you solve for it, negative 2 V2, and V2 is 3. Factor out the negative 2. Factor out V2. We have negative 2 and 1. And now if we choose the V2 to be something nice and even, we have V equal to negative 2 and 1. Since that is corresponding to this eigenvalues, we call this is subscript 1, corresponding to that eigenvalues. So that is first. Second, we have eigenvalues equal to 6. Do the same thing. Subtract 6 on the diagonal. That is a minus lambda I. Now it's times the vector v equal to 0 vector. So we have the system negative 4 and 2, 2 and negative 1. Reduce row echelon form. Negative 4, 2, 2, and negative 1. 1, and this is negative 0.5, 0, 0. Of course, this might take a little more work than it need to, but I think when we write like this, there will be less room for error. So we have V equal to V1, V2. V1 in this case is 0.5, V2, and V2. Usually, if you don't write like that, and then we try to write from the metric matrix, you might miss a negative sign here or there. But anyway, factor out V2, you have 0.5 and 1. Now if we choose V2 to be something nice, like 2 times 0.5 is 1. So we don't have to deal with fraction or decimal. So just 1 and 2. And that is V, and we denote that as V2. So we have eigenvectors. Next, of course, we can just construct the orthogonal matrix P and the matrix D. Usually orthogonal matrix you call Q. Anyway, construct P and D. The matrix D first is very easy. D is just have lambda 1, 0, 0, lambda 2. Just stack the eigenvalues 1, 0, 0, 6. For P, first we have to normalize it. So I normalize here. U1 is V1 divided by V1. V1 is negative 2 and 1 over the magnitude negative 2 square plus 1 square. So we have negative 2 over square 5, 1 over square 5. That is U1. Now normalize U2. Normalize V2 to get U2. 1 and 2 over square root of 1 square plus 2 square. So 1 over square root of 5 and 2 over square root of 5. With that, we can construct the matrix P, the orthogonal matrix, as u1 and u2. Negative 2 square root of 5, 1 square root of 5, 1 square root of 5, and 2 square root of 5. Right, so just that. Next, I'll compute the quadratic form x transpose a x for this. Of course, if we just multiply this straightforward, that should not be any problem. But let's just, so x transpose a x. Right. So x transpose x1, x2, x3, the matrix A, 9, 3, 0, 3, 1, 5, 0, 5, negative 2, times x, x1, x2, x3. Right, I'll multiply these two first. That gives us still x1, x2, x3. Now multiply these two first. 9x1 plus 3x2, x3 0. Next 3x2 plus 1x2 plus 5x3, 0, x1, 5x2 minus 2x3. Now multiply this again, we have 9x1 square, row times column the first with the first, plus 3x1 x2. Now we'll do second one, 3 row times column, so x2 times this, this is x1, 3x1 x2 x2 square, and then 5 x2 x3, and now x3 times this, 5 x2 x3 minus 2 x3 square. So combine like terms, 9x1 square plus 6 x1 x2 plus x2 square plus 10 x2 x3 minus 2 x3 square. Actually, there's a faster way to do this. If we just look at this, the 9, first row, first column, x1, x1. The 3, first row, second column, x1, x2. By the way, since this is symmetric, you're going to have twice of those, because one this side, one that side, so you have two of them. And then we have 1 on the second row, second column, so second row, second column. And then the 5 and the 5, second row, third column, because they're symmetric, it's going to double that. So pretty much anything on the diagonal will be the square, and anything that not on the diagonal, we just do half of it, and then we just square it, multiply by 2, sorry. So it's going to be 3 x1 x2 times 2, and then 5 x1 x2 times 2. It is symmetric, so we don't have to do the other side. So combine like terms, that's what we have. Right, next, make the change the variable x equal to b py, so that transform the given quadratic form into quadratic form with no cross product if p and the new quadratic form. Right, so first from here we should write that as the matrix as this form. So from here we say it's going to be x transpose a x, where just like the last problem in reverse, we can say a is equal to, if it is diagonal it is fine, if it is not we have to split in half. Right, so that is the matrix A. Right, so the square on the diagonal and that split in half because it's symmetric. It's going to be double to 3, double to 5 here. Right, so same thing, eigenvalues, eigenvectors, and all of that. Right. Now, 1 eigenvalues determinant of A minus lambda I equal to 0. So that determinant 4, 2, 2, 7 minus lambda equal to 0. So cross product 4 minus lambda, 7 minus lambda minus 4 equal to 0. So that gives us 28 minus 4 minus 7 minus 11 lambda plus lambda square minus 4 equal to 0. So that gives us lambda square minus 11 lambda plus 24 equal to 0. And so 11, so that's 3 and 8. So lambda equal to 3 and lambda equal to 8. Right, so 2 eigenvalues. Next, find the eigenvectors. Right, so eigenvector is A minus lambda I times V equal to 0. Right, so first for eigenvalues of 3, the matrix 4, 2, 2, 7 minus 3 times V equal to 0. So make the romantic matrix 1, 2, 2, 4. This is easy. Reduce to echelon form. Give us 1, 2, 0, 0, 0, 0. So V1 plus 2V2 equal to 0, and V2 is 3. Let's just copy what we have earlier. So with that we have V equal to V1 is negative 2V2 and then V2. Factor out V2 we have negative 2 and 1. So we have the vector negative 2 and 1 and make that as V1. And since we're going to find the orthogonal matrix, we're going to normalize this. U1 is equal to V1 over V1 magnitude. Right, so negative 2 and 1 square root of negative 2 square plus 1 square. So negative 2 over square of 5 and 1 over square of 5. Right. Now, for lambda 2 equal to 8. Four minus 8. 2. 2, 7, and minus 8. Times v equal to 0 vector. So we have -4 and 2, 2 and -1. Sorry, this I don't have enough large space here, so I have to write very small. Right, the usual echelon form of this guy. Yeah, actually just the right side just 0, which we just need 2 by 2 here. -4, 2, 2, and -1. So v1 minus 0.5 v2 equal to 0. v2 is 3. So v is equal to 0.5 v2, and v2 is 3. Factor out v2, we have 0.5 and 1. Right, now if we choose v2 to be something that we eliminate all the decimal, so that will be 2. So be 2 times that is 1, 2 times 1 is 2, and that is v2. Since I'm going to find the orthogonal matrix, I'm going to normalize this. u2 equal to v2 over magnitude of v2, 1 and 2 over 1 square plus 2 square. So we have 1 over square root of 5 and 2 over square root of 5. Right, and then finally, now if we write x transpose ax, and a we're going to write as q dq transpose q inverse x. That means this can be y of course, because q is orthogonal, so q inverse is the same as q transpose, so we can just write transpose here. Right, so y is equal to q transpose x. Y equal q transpose x. So x is equal to the inverse of that, so q y. Yeah, so in that case I use q instead of the question as for p. So in that case, finally the matrix is lambda 1. So from that case, we can say this is 3y1 square plus 3 plus 8y2 square, because that is just the eigenvalues on the diagonal, and that in the quadratic form corresponds to that. And then the matrix Q is just stacking this together. So the matrix Q is going to be negative 2 square root of 5, 1 over square root of 5, and then 1 square root of 5, 2 square root of 5. Yeah. So that is the matrix P or matrix Q. If we orthogonalize it using the normal vectors, we can just say it in this form. So we have y equal to q transpose x. So multiply the inverse on both sides. Inverse of q transpose just q. So x equal to qy. Right? So once again, because this is a symmetric matrix, the eigenvectors are orthogonal. So we know they are orthogonal. All we need to do is normalize it. Then we have the q. And so A is equal to Q dQ transpose of P d P transpose. And then we just pretty much have that. And with that, we complete all the review for linear algebra. Thank you for watching.